So good evening, all. Today we are at the session number 8, that is problem solving session number 8 for the course Biointerface Engineering. So this is basically the last uh, live session for this semester's run of this particular course. So as you all know, the course instructor is Dr. Lalit Mohan Pandey, is the associate professor in the Department of Biosciences and Bioengineering, IIT Guwahati. I am Shilpa Nandi. I am the PMRF in Center for the Environment, IIT Guwahati itself. So basically, we are going to go through a recap of the week 8 course content, and as well as then go for the problem and question solving session. So if you have any doubts during the session, you can again raise your hand, unmute yourself and raise the query, or the questions can be posted in the chat box also. So there is a discussion forum for the course available in the portal. So any questions regarding this particular session other than that other week course, you can just post your query there. So the questions will either be addressed by a course member, or even you can in the live session as well. So this is the last live session, so probably the questions will be addressed in the forum itself. Right, so we'll move on. So this particular live session will contain again the week 8 course content recap, which will consist of these last three lectures, that is lecture number 22, surface characterization, lecture number 23, self-assembled monolayers, and lecture number 24, that is effect of self-assembled monolayers on biointerfacial interactions. So next we'll go through week 8 related assignment questions and the answer discussion. So we'll go through a quick revision of the week 8 course content. So in lecture number 22, we basically discussed what are the various techniques for surface characterization. Basically, two kind of techniques were focused on. One is microscopic techniques and another is spectroscopic techniques. So in case of microscopy, in we use a microscope basically to view objects in the range of millimeter to nanometer, right? So microscopy can be categorized into optical microscopy, either then we have electron microscopy, then there is scanning probe microscopy, field emission or ion microscopy, and lastly it is low energy electron diffraction. So low energy and electron diffraction also may involve the X-ray, um, that is basically the X-ray involved microscopy, right? So if you see the resolution power, so as we go into the complex microscopy techniques, so the resolution is lesser, right? So you can see 500 nanometer is for optical microscopy, then for electron it is 1 nanometer, scanning probe it is less than 1 nanometer, and field emission or ion microscopy it is 3 to 5 nanometer, and lastly 0.01 to 10 nanometer. So uh, the lesser the resolution, the more uh, better is the view of the image, right? So for optical microscopy, again, it can be divided into light microscopes and confocal microscopy. So light microscopy again involves various other microscope like bright field microscopy, dark field microscopy, even phase contrast microscopy. Then there is uh, dark phase contrast microscopy, as well as fluorescence microscopy also comes under light microscope. Whereas electron microscopy, if you see, we have SEM and TEN. So SEM is scanning electron microscopy, whereas TEM is transmission electron microscopy. So we'll go through few of these microscopy techniques in detail, as it was taught in the course. So for in case of light microscopy, it is basically based on this Rayleigh formula. So 2 point objects separated by a distance s. So the resolving power or the Rayleigh criterion, that is x, is given as 0.61 lambda by numerical aperture. So here you can see lambda is the wavelength of the incident light and numerical aperture is n sine eta sine alpha. So eta is your refractive index of the medium and alpha is the half angle subtended. So from this equation you can see that the Rayleigh criterion or the resolving power x is actually inversely proportional to the numerical aperture, which is again you can say that this resolving power is inversely proportional to the refractive index as well, right? So in case of confocal microscopy, it has the ability to scan to 3D scan. Okay, so in case of confocal microscopy again, so very thin samples or skin based samples like skin can be also assessed through this confocal microscopy. So in case of scanning electron microscopy, in this case an electron beam is directed toward the specimen instead of the light beam. So in case of light microscopy we are using a light beam, whereas in case of scanning electron microscopy we are using an electron beam. So it is highly concentrated and is shot from an electron gun located at the device top, and it strikes the specimen surface and interacts with the surface. So these electron emission from the surface like X-rays, backscattered electrons, primary that is the primary electrons or the secondary as well as auger electrons are being scanned or read by the scanning electron microscopy. So in case of SEM mainly we have backscattered or secondary electrons which are being assessed. Okay. So if we move forward and go to 10, we can see in this case beam of electrons is transmitted through the sample. It's not just scanned, but it's transmitted through the sample to form an image. So diffraction of the electron beam occurs once these electron is transmitted to the sample, and this diffraction intensity again varies depending upon the plane's orientation with respect to the electron beam. So blocking the deflected electrons allows the unscattered electrons to go through it, which is actually used to obtain the contrast image in case of light field image, whereas in case of dark field image deflected electrons again can be also used to form a dark field image. So in this case, this TEM has a limitation, that is, it is only limited to thin films. So that's why we move on to next technique of microscopy, that is scanning probe microscopy. So it can be either scanning tunneling microscopy or AFM, that is atomic force microscopy. In case of STM, exponentially decaying tunneling current between the metal tip and the conducting surface is assessed, whereas in case of AFM, deflection is cantilever arises due to the capillary electrostatic or van der Waals, even frictional forces between the tip and the surface. So basically, AFM measures the surface energy in the range of 10 power minus 13 to 10 power minus 16 Newton. So AFM basically it acquires an image in the 3D topography and provides a kind of surface measurement. So in this case, uh, the components basically involves a piezoelectric cantilever which has a sharp tip that can scan the surface of the sample. Again, there is a cantilever present, and as the surface approaches the tip, a small deflection is observed in the cantilever towards the surface. This is because of the attractive forces between the tip and the surface. Now, the cantilever's deflection away from or the movement toward the surface is again detected using a laser beam. So, laser beam is one another component, and the deflection of the cantilever is then recorded by a photodiode. So the detector is basically this photodiode detector, and AFM again, as I said, it measures the surface force in the range of 10 power minus 13 to 10 power minus 16 Newton. So if we go on, we have spectroscopic techniques, various techniques like involving electron, photoelectron, infrared spectroscopy. or even ion scattering spectroscopy are used for surface characterization. So in this case, surface is irradiated with a probe of either photons, electrons, ions, or the combinations of it. So we'll see what are these various spectroscopy technique. One of them is XPS, that is X-ray photoelectron spectroscopy. So in this case, it is a surface sensitive technique which analyzes surface chemistry up to 1 to 10 nanometer thickness of the material. So this particular XPS provides elemental analysis as well as chemical and electronic states of the element, density of the element as well. So in this case, in XPS, a continuous beam of the monochromatic X-ray is basically radiated at the sample. The sample emits the electron from the surface and then the kinetic energies is measured. So the measured kinetic energy and the binding energy, the elemental diffraction and chemical state are then determined. So this binding energy is basically equal to energy of the photon minus E kinetic energy plus phi. So this phi is actually the minimum energy required to eject an electron from an atom. So if you see it's in bracket, so if you open it, it will be actually E photon minus E kinetic again minus phi. So this minimum energy required to eject the electron from an atom will be again subtracted to get the binding energy, right? So basically in this XPS, we calculate the total energy of the electrons ejected, which determines the composition of the material. So the number and the intensity of the peaks from an element reflects the characteristic energies and are used to identify with the standard database to explore the composition. Again, in this case, there is a chemical shift which is involved. So this particular chemical shift is referred to as the change in the binding energy of the core electron of the element, which is due to the alteration in its chemical bonding. So you should remember this, what is this chemical shift and how does it occur. So if we go on and we see, we have X-ray diffraction also as one of the methods. So this is basically a non-destructive method to analyze the crystal structure and the unit cell dimensions of the material. So in this particular XRD, a monochromatic X-ray beam, as you can see from the figure, an X-ray beam is okay. So in XRD, as you can see, a monochromatic X-ray beam is incident on the material there. So this, when the X-ray beam falls on the material, it produces a constructive interference from the diffracted rays. So this particular diffracted rays are detected by a detector, and this is basically based on the Bragg's law. So what is this Bragg's law? Bragg's law is expressed as n lambda is equal to 2d sine theta, wherein n is a positive integer, lambda is the wavelength of the incident wave, and d is the interplanar spacing as well as theta is the angle of incidence. So mostly in case of these XRDs, the X-ray source is used, that is CUK alpha, which has a wavelength of around 1.54 angstrom. So any particular question can be asked while you are giving in any of in your exams, like which can be based on this particular X-ray source XRD. So in that case, you must remember what kind of X-ray source is used. So in that case, the lambda won't be given. So you must remember this. What is the wavelength, particularly for these kind of X-ray source, which is around 1.54 angstrom. Okay, so XRD have various applications like peak positions, intensity, or shapes. All these can be analyzed. So this is given in detail in the course as if you go through the videos. So next we have FTIR. So FTIR is Fourier transform infrared spectroscopy. So in this case, works based on the bond vibrations for the absorbed infrared radiation in the particular wavelength region is used. So near IR infrared region is around 1 to 2.5 micrometer. In case of mid IR region, it is 2.5 to 25 micrometer. Whereas in case of far IR region, it is 50 to 1000 micrometer. So you must remember that in case of FTIR, basically it works between this mid-IR region. So this mid-IR region, I can underline it if you want. So that is 2.5 to 25 micrometer, and then there are peaks are formed, or we get peaks which can determine what kind of secondary structure the particular sample has. In case of Raman spectroscopy, again, Raman scattering or inelastic scattering, this uses monochromatic laser light to analyze the rotational, vibrational, and other modes of molecules in the system. So this particular Raman scattering or Raman effect is due to the interaction between the photons. Sorry. So interaction between the photons and the laser light results in the shift in energy, which provides information about the vibrational modes. So laser beam will illuminate the sample, and radiation from the laser hit the spot collected with lens and pass through the collimator. So molecules get excited to higher energy level and is relaxed into a vibrational excited state, resulting in a Stokes-Raman scattering. So you can remember the principles and several applications of it. Basically, principle, if you know what are the principle, or you can again go through various pictures which is already present in the internet to read more about this kind of spectroscopy. Okay, this was about lecture number 22, that is surface characterization. So next it was lecture number 23, that is self-assembled monolayers. In this particular lecture we discussed what are these self-assembled monolayers and how it is basically formed. Self-assembled monolayers are highly oriented, ordered and 2D molecular arrangements over a surface. So these particular SAMs have high specificity towards particular substrate that cause spontaneous adsorption of the SAM molecules. Okay, so covalent linked on the surface and does not deteriorate the bulk properties. So this is a very big characteristic of these SAMs, that it does not deteriorate the bulk properties, for which it is very much used. Okay, so this was introduced in 1947 by Zisman et al. And Sagiv et al. In 1980 showed that SAMs of organosilane on silicon surface. So name is given due to its ability to assemble themselves into the monolayers. So how these SAMs are basically formed? It contains basically four components. So if we go from top to bottom, let us go from bottom to top. If we go from bottom to top, we first have a metal surface. So this metal surface above which had a ligand or the head group. So the interface between this ligand or the head group and the metal surface is basically what stabilizes the surface atoms. Also, it modifies the electronic states. As we move forward, we have a spacer. Spacer is made up of various alkane chains. So this spacer provides a well-defined thickness. You have to remember all of these properties. What does these components relates to? Okay. So this acts as a physical barrier and it alters the electronic conductivity and local optical properties as well. Next, above which, that is at the top of these SMs, we have the terminal functional group. So this particular functional group actually what is determines the functionality of these SAMs. So it determines the surface properties and presents the chemical functional group. Right. So this particular figure is of very much importance. So you must remember what are the components of these SAMs and what functions do they hold. Okay. So there is this interaction between the surface and modifying agent. This is two kind of interaction is present. One is physisorption, another is chemisorption. So in case of physisorption, the enthalpy is around less than 10 kcal per mole, whereas in case of chemisorption, the enthalpy is greater than 10 kcal per mole. So physisorption basically includes interaction like van der Waals forces, and you can see from the enthalpies that chemisorption is more stable than physisorption, right? Because the enthalpy is higher than that of physisorption. Okay, moving on. So this is an example like organosilane SAMs on silicon surfaces. So you can see it basically there is two processes. So covalent attachment occurs on the hydroxylated surface. The process starts with the hydrolysis of the silane molecules, and then moving forward there is a formation of the strong siloxane, that is SiO-Si bonds. So I can show you through this. So this, so you can see. So process start with the hydrolysis of the silane molecules, and here we have your uh, this is your ligand. This is silane group, and this is your spacer, and this X is basically your functional group, right? So functional group is what was present at the terminal end. So this is what we studied in the last slide, which was shown that how a SAM or SAMs are formed. So we have various type of SAMs. So based on the type and the reactivity of the substrate surface, ligand head groups are altered. So in case of so this particular picture is not visible. Let me just okay. So in case of glass or silica surface, we use silica group. Okay. In case of gold surface or in case of silver surface, we usually use thiol group as the ligand. Then in case of metal oxides, catechol containing groups are used. So you can see, for example, silane group is used in case of silica or glass. In case of gold surfaces, thiol dialkyl sulfides are used. Again, in case of glass, gold, or metal oxides, various macromolecular polymers can be used. So, depending on the type and reactivity of the surface, substrate surface, ligand head groups are altered. So, you cannot use similar kind of ligand head for each type of substrate surface. So, pertaining to this, so the influence of terminal groups, so you can either have single or mono SAMs, or you can even have mixed SAMs. So in case of mono SAMs, there is single type of terminal functional group, that is R1SH. And in case of mixed SAMs, we can have different functional groups present at the terminal end, like R1SH. Like in one of the SAMs, R1 is the functional group, whereas in another R2 is the functional group. So I can mark it here, like, so you can see, so this can be R1, this is R2, R1, R2, R1, right? So you can have both single or the mono SAMs with containing single type of functional groups, whereas in you can also have the mixed SAMs. So in case of mixed SAMs, co-adsorption of different types of alkane thiols in this case occurs. So as I said, different kind of substrate or different kind of substrate present helps you to choose different kind of ligand head. Right. So here several molecules like alkyl acids, thiols, phosphonates, silanes are given referring to their particular substrate materials. For example, if the substrate material is made up of metal oxides like Al2O3 or AgO, alkyl acids like RCOOH is used. Similarly, if the substrate material is silica, hydrated or oxides, silanes group are used. So the attachment over the surface may occur via different routes and molecules, and the bonding energy decides the strength and thus the stability of the attachment. So from this table, you can see the highest bonding energy can be seen when there is selenization process. Bonding type is covalent with the molecule silanes, and substrate used is silica or silica hydrated. Right, so the energy is around 443 kilojoule per mole. So depending upon what kind of the substrate surface or the ligand head is used, so the strength or the bonding energy decide the strength and thus the stability of the attachment. So various factors affects these formations of these SAMs like water. So as you see, this particular reaction is condensation reaction. So water is absolutely necessary. If there is an absence, so there will be an incomplete attachment. And if there is excess of water, so this polysiloxane bonds formation in solution will form. So temperature again, higher temperature or lower temperature than that of the threshold temperature can cause difficulty in the formation of these SAMs. So a threshold temperature must be present. So temperature close to Tc is required, which is related to the alkyl chain length, and above this Tc monolayer formation is inhibited and again may yield dense packing. Similarly, concentration of the modifier and the reactive agent is also one of the factors that affect the formation. Choice of the solvent, and again the reaction time. So the reaction time also affects how uh, how stable your SAMs are formed. So next we have this kinetic study of attachment and reorientation of octyl triethylene for formation of SAM on a silica substrate. So you can see this is one of the examples how the SAMs are formed. So kinetic studies have also been done regarding this similar thing. So formation of SAMs basically consists of, in this case, silica surface plus silane. First process is your attachment and next is your rearrangement. So the rate constant K1 during the attachment and the K2 during the rearrangement. So this is how you can also determine the kinetics of these formation. And experimentally, if you perform the formation of these SAMs, you can go for assessing the surface topology and roughness through AFM. You can go for assessing the surface wettability through WCA analysis, that is wettability analysis. Then film thickness can be assessed using ellipsometry. And again, functional group studies at different intervals can be done through FTIR. Right. So similarly, the effect of modifications on these interface properties, as already we discussed in the previous slide, like wettability, surface energy, surface potential, and surface roughness can be assessed. So any modified surface definitely change the wettability properties. It can change the surface energy, can change the surface roughness as well as the surface potential. So in this table, you can see wettability or surface energy of some of the SAMs are given. For example, mixed silence use like APTS and TEOs in the ratio of 1 is to 1, and with head group containing mixture of NH2 and CH3 groups have these particular surface wettability, surface energy, and surface roughness. See, various SAMs have been compared here with respect to their surface wettability, energy, and roughness. So next we have this last lecture revision left. So in this particular lecture, the effect of SAMs on biointerfacial interactions have been taught. So basically two of the examples were given, and one of them is like surface functionalization of titania via SAMs for improved protein adsorption and fibroblast adhesion. So in this case, titanium surface modification and characterization has been done for protein adsorption involving BSA and fibronectin as well as fibroblast cell adhesion. So why do we do this surface modification of titania? This titania and titania alloys are actually widely used in orthopedics and dental applications. So it possesses desired mechanical property like low elastic modulus, good fatigue strength, lacks osteointegration and osteoconductivity, and the surface modification improves physiochemical and biological interaction at biointerface. So at the end of the day, what do we basically focus on the biocompatibility if we are going for the orthopedics or dental application, if we are using such kind of surface modified surfaces, right? So titania surface were modified using amine, octyl, and mixed hybrid and carboxyl SAMs. So various studies were done, and like in this case, like monotype SAMs containing amine and carboxylic group, mixed SAMs containing both amine and octyl group, and hybrid SAMs containing amine surfaces in p-tolyl isocyanate solution, that is urea linkage. Okay, so at the end it was seen that surface engineering basically regulates the biointerfacial interaction and thus tunes the performance of the biomaterials. So FN adsorption, that is fibronectin adsorption in case of hydrophobic substance, surface hydrophilic substance, or moderately hydrophobic substance are very different. So you can see various different surface have different cell adhesion and also different wettability properties. Like in case of moderately hydrophobic surface, we have a contact angle of around 82 degrees. So it basically uh, from hydrophilic surface, it increase in the surface hydrophobicity is seen, and also cell adhesion occurs. So that is what we are basically focusing on to, that surface engineering can regulate these biointerfacial interaction and helps to tune the performance of these biomaterials. One another example was also being studied in this particular lecture, that surface modification of Ti6Al4V by forming hybrid SAMs and its effect on collagen 1 adsorption, osteoblast adhesion, and integrin expression. So titanium surface was modified by forming hybrid SAMs and characterization. Then protein adsorption, that is the collagen 1 adsorption was studied. Then its osteoblast cell adhesion and integrin expression was studied. So percentage of cell adhered basically helps to know how well your modified surface is working. So for this particular case, you can see when you modify the surface, you have increased collagen 1 adsorption and again increased cell adhesion and proliferation. So this particular modification was done by a selenization, right? So next, so this is basically what was being uh, concluded in this lecture 24. So this completes all of your modules of the course Biointerface Engineering. So next we can move on towards solving the questions. So in today's session, as I said, we will be solving questions that are related to the assignment 8. So they are not exactly the questions which are available right now uh, in the session in your portal, but similar questions we can go through it. So first question is, which among the following microscopy techniques has the lowest resolution? So your options here are: A is scanning probe microscopy, B light microscopy, C field emission microscopy, and D low energy electron diffraction. So you have to say in terms of lowest resolution, which among the following microscopy techniques has the lowest resolution? So I'll give you a few minutes. So any guesses if you can? So we already discussed in the recap of lecture number, yes, lecture number 22. Right, so the lecture number 22 actually begins with this microscopy techniques itself, and the second or the third slide only has this particular information given. So yes, likewise. So I have got an answer, that is B, that is light microscopy. Okay. So let us see what's the answer to it. So yes, B is the correct answer. Which so light microscopy among all these four options have the lowest of resolution. So if you reverse the question, and if I ask that which among the following microscopy techniques has the highest of resolution, you can just compare through the given table and you can also answer that particular question. So if you say which among the following microscopy techniques has the highest resolution, the answer would be again low energy electron diffraction. Okay, so anyway, any kind of question can come. So yes, microscopy, various microscopy like optical, electron scanning probe, field emission or ion, and low energy electron diffraction have various resolution. So as we move ahead, like forward, so optical microscopy has the lowest resolution, that is of 500 nanometer, uh, whereas in case of low energy electron diffraction, highest of resolution can be seen. Okay, so optical microscopy again involves light microscope and confocal microscopy. Okay, let's move forward with the next question. So which among the following is true for Rayleigh equation for an optical microscope? The resolution power is inversely proportional to the numerical aperture. B. The resolution power is directly proportional to the numerical aperture. C. The resolution power is exponentially proportional to the numerical aperture. And D. None of the above. So if you can recall back what was this Rayleigh equation and where particularly did we study this? C. So I've got an answer as C. So you will see what's the correct answer is. So I have got option A also as the answer. So can anyone say, just tell me what is this Rayleigh equation, or can anyone or even can write it in the chat box if you want, if you don't want to speak up. So the Rayleigh equation for an optical microscope is given as, how is it expressed basically? Okay. So we'll see the answer to it. So the resolution power is inversely proportional to the numerical aperture, is directly proportional to the numerical aperture, or is exponentially proportional to the numerical aperture. Right. So as if you recall, what is this Rayleigh equation? So Rayleigh criterion or the Rayleigh equation is given in case of the optical microscopy. We follow it, which is given as x is equal to 0.61 lambda by numerical aperture. So your numerical aperture stands for, again, it is directly proportional to the refractive index, right? So yes, the correct answer for this question would be option A, that is the resolution power is inversely proportional to the numerical aperture. So you can see 2 point objects separated by a distance x. So the resolving power is given as 0.61 lambda by numerical aperture. So x is equal to 0.61 lambda by numerical aperture. Lambda is the wavelength, and here the resolution power is inversely proportional to the numerical aperture. Okay, so I guess there is no doubt till now. So we can move on to the next question. So again, a similar question related to microscopy. So numerical aperture in terms of refractive index is expressed as, first is point numerical aperture is equal to 0.61 eta. B is numerical aperture is equal to eta sine alpha. C numerical aperture equal to eta sine lambda. And D is your numerical aperture is equal to eta sine 0.61. So it is a extension of your previous question. Basically, what is this numerical aperture? Okay, C. I have got one answer as C, that is numerical aperture is equal to eta sine alpha. Okay, we will see whether it is correct or not. But if any other guesses anyone has, you can obviously post it in the chat box. So, okay, as Uzma said, C, option C. So, is numerical aperture is equal to eta sine lambda. So, as if you go back to the last question, And recall what was it? It was basically as x is equal to 0.61 lambda by numerical aperture. So how come numerical aperture will here be directly proportional to your wavelength? So you can see, so in the previous question it was already said that x is equal to 0.61 lambda by numerical aperture, right? And you are saying that this is this should be the correct answer. So if you can change your if you can think a bit and then try to get the answer. So yes, you have to give numerical aperture in terms of refractive index. So which among these following expressions give the refractive index? So refractive index is basically expressed in terms of this eta here. Okay. So option C, I am ruling out option C for now. So you can answer me in between A, B or D. So it is not possible to have your option number C because we saw that the resolving power is directly proportional to your wavelength. So how come numerical aperture will be equal to eta sine lambda? Okay, so okay, let's see what's the answer is. So the correct answer will be option B, that is numerical aperture is equal to eta sine alpha. So x is your already, that is 0.61 lambda by numerical aperture. So option C, that is NA is equal to eta sine lambda. You can rule it out because it numerical aperture cannot be directly proportional to your wavelength. And we are left with A, B and D. So B is your correct answer. You can see numerical aperture is given as eta sine alpha, whereas eta is the refractive index of the medium and alpha is the half angle subtended. So you must remember what is basically this numerical aperture, and also numerical aperture is directly proportional to the refractive index. So any question can come from this particular formula. Just now I proposed two of the questions. One of the questions is already given in the assignment, current assignment. So other questions can also be framed. Right. So you must remember what basically is this Rayleigh formula and what is this numerical aperture and this refractive index, as well as differentiate between the wavelength. Do not confuse between the wavelength and alpha. So wavelength is directly proportional to the resolving power, whereas alpha is directly proportional to the numerical aperture. Okay. Um, is there any doubt till now? Okay, we will move on to the next question then. So again, which of the following is not a type of light microscope? So we saw optical microscope can be either light microscope or even confocal microscope. Here you have been asked which of the following is not a type of light microscope. Okay, I have already got one answer. Okay, but we'll finish the question first. So A option is your TEM, that is transmission electron microscopy. B is your dark field microscope. C fluorescence microscope, and D is phase contrast microscope. Okay, so I think you already know about this. So yes, you are correct. The correct answer for this question is option A, that is transmission electron microscope. So transmission electron microscope, scanning electron microscope, all these comes under the electron microscopy and not under optical microscopy. Whereas light microscope, you can see various bright field microscope, dark field microscope, fluorescence microscope, this phase contrast microscope, as well as dark phase contrast microscope is also there, which comes under light microscopy. Okay, fine. I can see that this is quite clear to you. So we can move on to the next question then if there is no doubt. Okay. So we will go to our next question, that is question number 5. So which of the following is true for confocal microscopy? So options here are A, increased optical resolution and contrast. B is facilitates 3D reconstruction of samples. C is allows surface profiling of samples, for example skin. Or D, all of the above. So confocal microscopy again comes under optical microscopy, and you have to tell me which of these is actually true for confocal microscopy. Whether does it increase it has an increased optical resolution and contrast, um, and whether it facilitates 3D reconstruction of samples or not, or whether it allows surface profiling of the samples, for example skin, or is it all of the above? Okay, I've got one answer, that is A. Okay, increased optical resolution and contrast. Okay, with you can say yes, it is true. If you compare it with other light microscopy techniques, confocal microscopy gives us a better optical resolution and contrast. What else could be true for this particular question? Basically, what we have seen is confocal microscopy also helps in 3D scanning of the samples. So it also facilitates 3D reconstruction of sample and also allows surface profiling of the sample, for example skin. So if we say that confocal microscopy has increased optical resolution and contrast, it also facilitates 3D scanning and also allows surface profiling of the sample. So which one would be the correct answer? Yes, okay. So D, that is all of the above. So all of these statements are actually true for confocal microscopy. So you must remember that this confocal microscopy, that is optical imaging technique using point illumination via a pinhole to eliminate out of the focus signals. So advantages of this is basically it increased optical resolution and contrast, facilitate 3D reconstruction of sample, allows collection of serial optical sections from thick samples, as well as allows surface profiling of the sample. So for this particular question, option D, that is all of the above, is correct. Okay, so any doubt till now? Wait for 2 minutes, then we'll move forward. So any doubt or question you have, you can again post it in the chat box. Okay, just give me 1 minute, or let me show you the second next question. We'll take 2 minutes break. Okay, so the sixth question is, which of the following types of electron emissions is employed in case of scanning electron microscope to examine the surface morphology? So you have to basically tell which of the following types of electron emissions is used in case of SEM to examine the surface morphology? So your options here are A. Backscattered electrons, B. Primary electrons, C. Secondary electrons, or D. All of the above. So one of the answers, that is C. Did anyone say C? Okay, yes. So I've got the answer as C, secondary electrons, but it is not the correct one. So you can try again. So what kind of electron emissions is basically employed in SEM, scanning electron microscopy? Okay, again A, backscattered electrons. Okay, we'll see what's the correct answer. I'll give you 1-2 minutes to rethink about it and then actually give me the answer. Till now, so okay, I got one of the answer as C and now I've got the answer as A, that is backscattered electrons. So any other guesses? I think you need to recall SEM properly, like scanning electron microscopy, and go through the lectures once again and look into it that what kind of electronic emissions are basically utilized. Okay, last 1 minute. If anyone has any other guesses. Okay, so actually the correct answer for this question is all of the above. So all of these backscattered electrons, primary electrons as well as secondary electrons are utilized or employed in case of SEM to examine the surface morphology. So if you see, the correct answer would be option D, that is all of the above. And if you recall back what was this SEM, you can see that electron emissions from the surface such as X-rays, backscattered. So backscattered again it is if you it is also called as primary electrons. So there is no difference between the backscattered and the primary electrons. So both option A and B, that is backscattered and primary, both were same. Then we have secondary electrons and Auger electrons. So at the last you can see it's written SEM makes use of the primary or backscattered and the secondary electrons. Right. So you must remember that what kind of electron emissions are being employed in case of SEM. So your answer would be option D, which is all of the above. Right. So any doubt till now? So backscattered and primary both are same. C is your secondary electron. So we have all of the above as the correct answer. Okay. So we'll go to our next question. That is question number 7. So we have, which of the following involve the limitations of transmission electron microscopy? So limitations of transmission electron microscopy has been asked. So your options are given here as A. Samples are limited to those that are electron transparent. B. Technique is limited to thin films. C. Both A and B, or D. Raw resolution and magnification. So first option, that is okay. Both Uzma and Amardeep are saying option C, that is both A and B. Okay, we'll see. So option A, that is samples are limited to those that are electron transparent. Yes. So what was the basis for transmission electron microscopy? Can anyone tell me? So what was the principle behind it? So in this case, like differing from that of SEM, in case of TEM, we have like transmission, or the electrons are transmitted through the surface of the sample, right? So the surface have to be electron transparent. So if the samples are not electron transparent, we cannot use it for TEM. So option A, that is samples are limited to those that are electron transparent, is actually a limitation of TEM. Then we have B, that is technique is limited to thin films. So in case of TEM, the sample preparation or the sample should be very thin. Then only the electron will be transmitted through the sample. So the correct answer, yes, you guessed it right, which is option C, that is both A and B. Both A and B, that is, are the limitations of transmission electron microscopy. Okay, so obviously raw resolution and magnification is not the correct limitation in case of TEM, because it has high resolution as well as magnification, right? So yes, if you go back through the lectures, you will find it's written here that this technique is limited to thin films, and also the beam of electrons is transmitted through the sample to form an image, thus the sample has to be electron transparent. So any doubt till now? Okay, let's move on to the next question then. So next question, that is question number 8. Chemical shift refers to A. The change in the structure of a core electron of an element due to alteration in its chemical composition. B. The change in the binding energy of the core electron of an element due to alteration in its chemical bonding. C. The change in the energy shift of a core electron of an element due to alteration in its physical properties. Or last, none of the above. So where did we read this chemical shift? You can, if you can just recall in which of the spectroscopy methods. So I can give you one of the hint that chemical shift refers to one of the spectroscopy methods or the spectroscopy techniques. So which of the spectroscopy techniques did we read about this chemical shift? Okay. So Usma is saying that answer A is correct. That is a change in the structure of a core electron of an element due to alteration in its chemical composition. Okay. So I may tell you that option A is actually not the correct answer. So it's like I've already said, one of the your options have been already ruled out, option A. So you're left with B and C. So if you see that chemical shift refers to, so in case of option C, it is written the change in the energy shift of a core electron of an element due to alteration in its physical properties. So do you think this alteration in its physical properties can lead to chemical shift? So this particular option, that is C, so it has this physical terminology. So if you see, you can also rule out this option. So the first option which you can have ruled out is this option C itself. That is, chemical shift actually does not refer to the change in the energy shift of a core electron, which is actually occurring to the alteration of in its physical properties. So A and B, as I said that A is also not the correct answer. So what would be the correct one? It is actually B. So chemical shift is actually the change in the binding energy of a core electron of an element due to alteration in its chemical bonding. And this particular chemical shift was actually, we studied it in case of XPS, X-ray photoelectron spectroscopy. Right. Let us go back and just see, revise once. Yes. So in case of XPS, as you can see, what do we do is we calculate the total energy of the electrons ejected. That helps to determine the composition of the material. So the number and intensity of the peak from an element reflects the characteristic energy and is basically used to identify with the standard database to explore the composition. So in this case, a chemical shift is being seen, which is actually referring to the change in the binding energy of a core electron of an element due to the alteration in its chemical bonding. So where does this binding energy actually comes from? So the kinetic energy is once measured and binding energy is also measured. So E binding is equal to E photon minus E kinetic plus phi. So what is this phi? It is the minimum energy required to eject an electron from an atom. So basically we are subtracting this minimum energy as well as the kinetic energy from the energy of the photon to get the binding energy. So again the chemical shift is actually referring to the binding energy change of a core electron due to the alteration in its chemical bonding. Right? So in case of XPS we saw this. Right? So the correct answer would be option B and not A. Okay. So any doubt till now? Okay. So we can go to the next question, which is question number 9. So which of the following laws is X-ray diffraction based on? So option A is Rayleigh law, B. Beer-Lambert law, C. Bragg's law, or D. Hooke's law. Okay, A. So, so what was this A that is Rayleigh law basically? Can you write it down if you don't want to speak? You can unmute yourself and tell me. So you have been asked that which of the following laws is X-ray diffraction based on, right? So you are giving me the answer as A. So can you tell me what was this Rayleigh law actually? Okay, so if you see, Rayleigh law is actually the basis in case of optical microscopy. So in light microscopy or in another optical microscopy, we saw this Rayleigh law working wherein uh, okay, so wherein the light beam is used, and what does that Rayleigh law basically gives? The Rayleigh criterion, that is x is equal to 0.61 lambda by numerical aperture. So this particular Rayleigh law does not actually is the basis for X-ray diffraction. So X-ray diffraction is a spectroscopic technique and not a microscopic technique. So Amardeep is saying that the answer should be C, that is Bragg's law. Okay, so why not B and D? Beer-Lambert law and Hooke's law. So can anyone tell me what is this Beer-Lambert law is, or what is this Hooke's law is? Okay, so if you know, yes, it is good for you if you know particular correct answer, Bragg's law of diffraction. Yes. So yes, Bragg's law, I get it. So what about B and D, that is Beer-Lambert law and Hooke's law? Do you have any idea about it? So okay, fine, we will discuss. So yes, as you are saying, the correct answer should be C, that is Bragg's law. So Bragg's law is actually the basis for X-ray diffraction and not Rayleigh law. So Rayleigh law is for optical microscopy, whereas Beer-Lambert law is actually defines the absorption of a particular sample. So absorption is directly proportional to the concentration of the sample multiplied by the path length. So Beer-Lambert law we usually use to determine the concentration of unknown samples. And in case of Hooke's law, do you have any idea of about Hooke's law? So Hooke's law is actually the basis for infrared spectroscopy. Okay. So yes, so the correct answer for this question, that which of the following laws is X-ray diffraction based on? So the answer is C, that is Bragg's law. Yes, so Bragg's law, that is n lambda is equal to 2d sine theta. So you must again remember what is this Bragg's law, wherein n is the positive integer, lambda is the wavelength of the incident wave, and d is the interplanar spacing, theta is the angle of incidence. So in case of XRD, what happens? A monochromatic X-ray beam is incident on the material, which produce a constructive interference from the diffracted rays, which satisfies the Bragg's law. In case of Rayleigh law, it is the basis for optical microscopy. Beer-Lambert law is used in absorption spectroscopy, whereas Hooke's law is used in infrared spectroscopy. Is it fine? Uh, any doubt? So apart from Bragg's law, you can also remember all other three, and what does it basically relates to, so that anytime if the question is reversed and been asked about other laws, you can answer those also, right? Okay, if there is no doubt, we can go through the next question. So we have our next question number 10. So what are the components of AFM? So what is this AFM particularly is? So AFM stands for, okay, we will see what are the options and then we'll continue. So option here are A, piezoelectric scanner, B, cantilever, C, photodiode detector, and D, all of the above. So what are the components of AFM? So what does this AFM stands for? Can anyone answer? So if you don't know what is this AFM particularly, then it would be difficult to answer the question. So AFM is basically atomic force microscopy, right? So you have been asked what are the components of this AFM, atomic force microscopy. So if you go through the lectures, you will get the principle of it. And if you want to know exactly how this works, you can again Google any of the images of AFM present in the internet to actually get an idea of how does it work or what components does it have, right? So okay, Amardeep said that answer is D, that is all of the above. So if anyone has any other guesses, otherwise we'll move on to the answer. Okay, fine. So the correct answer is actually yes, option D, that is all of the above. So an AFM has all of these three, that is a piezoelectric scanner, a cantilever, and a photodiode detector as its component. So if you can see from this figure what basically an AFM constitutes of. So general components, so it has a piezoelectric scanner, then which is again connected to a computer. Then you have a cantilever, you have a laser diode, a mirror, then there is a position sensitive photo detector, then a feedback loop and a probe tip as well. So all of the functions has been also explained very nicely in this particular figure. So you can go through it. So yes, the correct answer was option B, that is all of the above. Right. So let's move on to the next question. Again, similar questions related to AFM. So AFM measures the surface force in the range of A, 10 to the power minus 13 to 10 power minus 16 Newton, B, 10 to the power minus 16 to 10 to the power minus 20 Newton, C, 10 to the power minus 10 to 10 to the power minus 16, and D, 10 to the power minus 10 to 10 power minus 13 Newton. So I know this is actually a property of AFM and it is basically theory and you have to remember it. So while going through the lectures, if you go back to what was this AFM, then you can see, let me, so AFM is actually it measures the measures the surface force in the range of 10 to the power minus 13 to 10 to the power minus 16 Newton. So if you go through the lecture and if you see what was basically revised in AFM, so there is a point which says that it measures the surface force in the range of 10 power minus 13 to 10 power minus 16 Newton. So this is a property that you must remember. We were in question number 11, right? So now you can answer. So AFM measures the surface force in the range of, the correct answer would be option A, that is 10 to the power minus 13 to 10 to the power minus 16 Newton. Right. So there is nothing to actually explain. It's a basic property and you have to just recall it. Fine. If is there any doubt? Okay, moving on. We have next question, that is question number 12. Okay, so any doubt till now? Okay, so we have question number 12. So Raman effect is a scattering of A, atoms, B, photons, C, molecules, and D, protons. So Raman scattering or Raman effect is basically the scattering of atoms, photons, molecules, or protons. Question is not displaying. Okay, just wait a minute. Can you see now? So Raman effect is a scattering of atoms, photons, molecules, or protons. Is it visible now at your end? Okay. So any idea what should be the correct answer? So you have to basically read and actually understand the basic principles behind all these spectroscopy or microscopy techniques, so that obviously you can be easily able to give the answers. Okay. So B, so yes, B, that is photons, is the correct answer. So why photons is the correct answer? So Raman scattering or the inelastic scattering basically uses monochromatic laser light to analyze the rotational, vibrational, and other modes of molecules in the system. So what happens is laser beam illuminate the sample and the radiation from the laser hit the spot collected with lens and pass through a collimator. So molecules get excited to higher energy level and is relaxed into a vibrational excited state, resulting in the Stokes-Raman scattering. So what happens here is the interaction between the photons. So there is a spelling mistake in the lecture, the course that is already uploaded in the portal. So this is actually the interaction between the photons and the laser light that results in a shift in the energy which provides the information about the vibrational modes. So what happens is Raman scattering is basically, or Raman effect is basically due to the photons. Okay, so you have to just make sure that the fourth point, that is interaction between the phonon, it is not phonons, it is photons. Okay, interaction between the photons and the laser light. So this is actually the slide that is being taken from the content which is uploaded, that is the video which you see. So in that case also there is a mistake, or the spelling mistake is there. It shouldn't be phonons, it is photons. Okay, let's move on to the next question. If you all are satisfied or there is no doubt. Okay, we have our question number 13. So which among the following constitute the correct sequence of the parts of a self-assembled monolayer? So you have your four options: A, head group, spacer, functional group, metal substrate; B, metal substrate, terminal group, ligand and spacer; C, terminal functional group, spacer, ligand, metal substrate; and D, spacer, head group, terminal functional group, metal substrate. So you have to tell me that which of the following constitute the correct sequence of the parts of the SAM, that is self-assembled monolayer. So all of these four options have various parts of the SAMs, but there is a sequence by which it is basically arranged, either from top to bottom or from bottom to top. Either way you go, one of these option is correct. So try to recall back the structure of these SAMs, or the formation of these self-assembled monolayers. I'll give you 1 minute if you can try to answer. So any guesses? Okay. Okay, so let's see. If you don't have any idea of it, we will see what's the correct answer. So actually, I am getting something. So D. So you're saying D, that is spacer, head group, terminal functional group, and metal surface. So actually D is not the correct option. So we will look forward to it and understand why D is not the correct option. So the correct answer is option C, that is terminal functional group, spacer, ligand, and then metal substrate. So this is basically the order from top to bottom. Okay, so this is what a particular SAM or a normal SAM structure consists of. So you can see we have four parts of it. First is the terminal functional group, then we have spacer, then we have ligand, and lastly we have a metal substrate. So this is the top to bottom sequence. So I can mark it here so it will be easier for you. So 1, 2, 3, and 4, right? So the terminal functional group present at the top, which is actually inter having the organic interface, and it determines the surface properties, and there is a functional group present on it, so presents the chemical functional group. Whereas the second part, that is the spacer consisting of the alkane chain, it constitutes of the organic interface, that is around 1 to 3 nanometer. It provides the well-defined thickness, acts as a physical barrier, and alters the electronic conductivity and local optical properties. Next, we have this ligand or the head group. So head group basically attaches to these metal surfaces. So there should be also specificity, or various different metal substrate have, and various different substrate have specificity to different ligand, right? So we already discussed about this in lecture number 23 recap. And lastly, we have this metal substrate. So metal sulfur interface. So sulfur, as you can see, so in this case, ligand or the head group is denoted as sulfur. So metal sulfur interface helps in stabilizing the surface atoms, as well as it modifies the electronic states. So not just you must remember the parts or the correct sequence of the parts of these SAM, but try to also remember what all are the functions or the properties of these parts, right? So any question regarding one of the question can come like what exactly is the function of ligand or the head group, or what is the role of this terminal functional group, right? So try to remember all these points. So as you said, option D. So option D was having spacer, head group, terminal functional group, and then metal surface. So this is not the correct answer. So the correct would be option C, terminal functional group. Then we have the spacer, then we have the ligand, and we have the metal surface at the bottom, right? So as the question asked, you have to tell that which among the following constitute the correct sequence of the parts of a self-assembled monolith. It not just said that you have to uh, tell that which of these following options are the correct parts of the SAMs, but correct sequence also. So it can, and the options could have been in reverse, like from bottom to top also. Okay. So any doubt till now? So shall I move forward? Simple yes would also help. So no doubt yet, we can go to the next question, that is question number 14. So again, for the surface modifications, the silane group can be used over A, metal oxide, B, glass, C, silica, or D, both B and C. So as you saw in the formation of, or the structure of a SAM, you just saw that there is a metal substrate or a substrate, and over which we have the ligand, right, which connects to your spacer, and then okay, Usma is saying D, okay, we'll see spacer, and then we have the terminal functional group, right? So this substrate is very specific to particular ligand. So different substrate have, we have to use different ligands, right? So for in relation to that, we have this question that for the surface modification, if the silane group, that is the ligand, if we use as the silane group, what should be the substrate? Can be used over metal oxides? Can it be used over glass, silica, or both B and C? So this particular portion is available in lecture number 23. You can note it down if you want and just go through it. It's very nicely given over there. Okay, as Uzma said, option D, that is both B and C. Yes, you are correct. So, can you tell me if the substrate is metal oxide, what kind of groups can be used? Does anyone have any idea? Okay, so I will repeat the question. So, as Uzma said, option D is correct, that is both B and C, glass and silica. So silane group can be used over both glass as well as silica. Okay. So as I'm trying to ask, if glass and silica for glass and silica silane group is used, and if the metal substrate is your metal oxide, then what kind of groups can be used? So I've got that no idea one, and okay, let's see. So yes, the correct answer for this question is option D, that is both B and C. So for silane group, both glass and silica substrate can be used. Similarly, if the substrate is made up of gold, thiol or dialkyl sulfides can be used. Now again, the substrate, if it is metal oxide, catechol groups can be used. Right. So any other question can be also framed wherein it can be given as for the surface modification. The catechol groups can be used over, then the answer would be metal oxide. Right. Or the question can be if for the surface modification, the thiol or dialkyl sulfides can be used over, then your option would be or your answer would be gold. Similarly, glass, gold, or metal oxides as a substrate when it is used, ligand containing macromolecular polymers can be utilized. Right? So you have to just have a like go through it, then it is very easy to remember all of these. Apart from this table, there is one more table from which you can learn. Like similarly, if you see thiols molecules or thiol group can be used over Au, Ag and Cu, that is your gold, silver as well as copper. So and question can come as for the surface modifications, the thiol group can be used over. So all these options, that is gold, silver and copper, are correct. Similarly, if the question can come from for alkyl acids, then metal oxides. For silanes, again silica hydrated or oxides as the substrate material can be used. Right. So any doubt till now? I have tried to give all the tables and all the descriptions related to what the questions ask so that for at least for this particular question you don't have to go here and there. So any doubt? We'll move on to next question if there is no doubt. Okay. Let's see next question. That is 15. So we are left with three questions. We have two numericals also today at the end of the session. So we'll solve those also. So 15th question, that is which of the following factor affect the formation of SAMs? So A, water, B, reaction time, C, concentration of modifier and reactive groups, and D, all of the above. Factors that affect the formation of self-assembled monolayers. What should be the correct answer? It is a very straightforward question. C, that is concentration of modifier and reactive groups. And why not reaction time and water? So reaction time also actually plays a very important role for the formation of SAMs. If the for few of the modified surface or few of the formation can take longer duration, whereas few of those formation of SAMs can take shorter duration, right? So the reaction time, the optimum reaction time is very crucial for the formation of SAMs. And also, since this is actually a condensation reaction, okay, so water actually plays a very important role again. So the correct answer would be actually option D, that is all of the above. Okay, so various factors like water, so in its absence, there will be incomplete attachment, and if there is excess, then polysiloxane bonds will form in the solution. In case of temperature also, apart from these three, we have other factors like temperature and choice of solvent as well. So temperature must be also optimum, that is a threshold temperature must be maintained. So again, temperature close to the threshold temperature is required, and above the threshold temperature, monolayer formation is inhibited and may yield dense packing. Right? Then again, concentration of the modifier and the reactive groups, choice of the solvent, and reaction time. So all of these factors actually affect the formation of self-assembled monolayers. So is there any doubt? Uh, this was a very straightforward question. If you would have gone through the lecture slides, then it is very easy to answer. Okay, so shall I move forward? We have the next question, that is question number 16. Which of the following is a property of titanium and alloys? So why do we use this titanium and alloys in case of dental applications or even in case of orthopedics, right? So option A is low osteoconductivity, high elastic modulus, low fatigue strength, or high osteo integration. So one of the option is only correct, and which is actually true for the property of titanium and alloys. Rest other three are actually incorrect. So can you try to give the answer? So property of titanium and alloys. So does it have low osteoconductivity? Does it have high elastic modulus, low fatigue strength, or high osteo integration? So as Amardeep is saying, C, low fatigue strength. Do you really think that is it true for titanium and alloys? Does it have low fatigue strength, or is it false? Shouldn't it be high fatigue strength? B, high elastic modulus. So, Uzma, do you think that titanium and alloys, when we use in case of orthopedics, do you know what is orthopedics? Like knee replacement, like people who have osteoporosis, like uh, they have this replacement, or in case of dental applications, do we want the dental application to have high elasticity? Um, or the knee replacement that we are having, we want it to be high elastic strength or low elastic strength? High, okay, Amardeep is now saying it's D. So all of the option basically you are saying like B, C, D, high osteo integration. Ost uh, So do you think we want a high osteointegration? Actually, osteointegration, osteo refers to osteocytes, like the bone cells, right? So bone cells are actually osteocytes. So do we want high osteointegration when we are using knee replacement made up of titanium and alloys? So we are now only left with option A, that is low osteoconductivity. Okay, fine. So you have tried all your luck with B, C and D. So the correct answer is actually option A, which is low osteoconductivity. So which of the following is a property of titanium and alloys? It should be low osteoconductivity. So titanium and titanium alloys are widely used in orthopedics and dental applications. So it should possess desired mechanical properties like low elastic modulus, good fatigue strength. So here it was actually high elastic modulus and low fatigue strength. It should have been the opposite. Then we have lack in osteointegration and osteoconductivity. So this should be actually low osteointegration and low osteoconductivity. It shouldn't be high osteointegration, right? So only option which was actually correct and which is actually a property of titanium and alloys among all these four was low osteoconductivity, right? So titanium and titanium alloys are actually widely used in orthopedics and dental application, and it should actually have low osteoconductivity, low elastic modulus, good fatigue strength and low osteointegration. So not just for low osteoconductivity, you must remember what are the properties of this titanium and alloys. Is it understandable so that we can move forward if there is no doubt regarding this question? Okay. So next question is a numerical. So for a CUK alpha based XRD measurement, calculate the incidence angle theta if the D spacing is 1.54 angstrom. You have to basically calculate the incidence light theta, and this is basically an XRD experiment. So if you recall back, what was the law which was this XRD based on? Bragg's law of diffraction, as you said, right? So if you write down the Bragg's law of diffraction and try to solve the question. So you are already being given the D spacing, that is 1.54 angstrom, and you have to determine what is the incidence angle theta. Can you calculate and tell me the answer whether it is 30 degree, 40 degree, 55 or 60 degree? So I've already given you a very big hint. What law is it based upon on? And the correct answer here would be 30 degrees. And as you can see, Bragg's law, that is n lambda 2d sine theta A. Okay, A is the correct option, I get it. We'll solve it because not everyone is able to solve the answer. So typical X-ray source, as I said, in case of CUK alpha with lambda has the value of 1.54 angstrom. Okay, so let us solve this. So Bragg's law is equal to n lambda is equal to 2d sine theta. So from the question we already have this d spacing. So d is our 1.54 angstrom, and we have to determine what is this theta, and we know for X-ray source utilizing this CUK alpha we have lambda of 1.54 angstrom. So if you put n is the positive integer, so if we take it as a positive integer and we place all the values 1.54 to d, that is 1.54 again, and sine theta. Right. So you have to calculate this. So not everyone is able to calculate it so easily, so that's why. So sine theta would be 1.54 divided by 2 into 1.54. Right. So if you cancel this out, 1 by 2 is equal to, how much is it? 0.5. So theta would be sine inverse 0.5. So how much would be the answer? Oh, so if you take your calculator and try to solve, how come 45? Sine inverse 0.5 is how much? 45. You already gave the correct answer. Okay, someone said A. Rajat, okay. Rajat said A and Amardeep is saying 45. How come sine inverse 0.5 is 45? Just take your calculator in hand and check whether sine inverse 0.5 is 45 or 30. Can you verify whether it is 30 or 45? So it is actually sine inverse 0.5 is 30 degree. So don't confuse even if you know the answer. Okay, it's 30. Fine. So is the slide visible? Because I just lost my connection for a few seconds. If the slides are not visible, please you can write it down in the chat box. So now is it okay? So okay, we will move on. Explain again. Okay, the same question from starting or the solution. Okay, I'll write it down once again if you want. Just let me add a new slide here. So okay, you just saw that this was based on Bragg's law, right? What was this Bragg's law? Amardeep? So it is actually n lambda 2d sine theta. Right. So we have this n as the positive integer, lambda is your wavelength, which in case of X-ray source, if you are using copper K alpha, then this lambda would be 1.54 angstrom. And from the question, this D spacer is given value 1.54 angstrom. So you have to basically find out what is this theta. Is it understandable till now? Yes. So just you have to place the values and try to solve it. Okay. So 1.54 lambda, that is lambda is equal to 2d 1.54 and sine theta. Okay. So now just sine theta would be 1.54 divided by 2 into 1.54. So this will cancel out. What you will be left is sine theta is equal to 1 by 2, which is 0.5. So sine theta, if it is 0.5, so theta will become sine inverse 0.5. So theta will be, sorry, so theta will be how much? 30 degree. So is it good for you, or any doubt is there yet? It's understood. Okay, fine. If it is actually as an easy question, simply you have to put the values and go for solving it. Okay, we have the last question. We are moving actually to the last question, which is a mixed surface of A and B is designed with the water contact angle of 75 degree. So this mixed surface has a water contact angle of 75 degree. This you can understand. Now the water contact angle on A, so this mixed surface is already having two different kind of surface. One is A and suppose one is B. So this A surface has a WCA of around 110 degrees, whereas this B surface has the WCA or water contact angle of 50 degrees. Right. So you have to estimate the fraction of A in the mixed surface. So how much will be the fraction is A, option A is 0.58, option B is 0.39, option C is 0.40 and option D is 0.65. So are you able to understand the question? Then I will give you one hint so that you can solve it further. Okay, so let me give you the hint for this question. So the answer would be option B. Okay, so it is actually based on, you have to solve this question on the basis of Casey equation, which is cos theta is equal to f1 cos theta 1 plus f2 cos theta 2. So f1 is your fraction of the compound 1 and cos theta 1. Theta 1 is the contact angle of surface 1, whereas f2 is the fraction of surface 2 and cos theta 2, theta is the contact angle of surface 2. So here in the question it is uh, like said as A and B surface. So Casey equation cos theta is equal to f1 cos theta 1 plus f2 cos theta 2 is actually basically used for solving this question. So all the information you are already given. Like you have the mixed surface water contact angle, you have the contact angle for surface A, then you have the contact angle for surface B. You have to estimate the fraction of A in the mixed surface. Also, the correct answer is 0.39. So if you are able to solve it, please let me know. Okay, let us try to solve this question. So what we have is, I already told you Cassie equation is the basis, right? So what we have is cos theta is equal to, now I can write it as FA cos theta A plus FB cos theta B. Can I? For this particular question, since the mixed surface is containing A and B surfaces, so FA cos theta A and FB cos theta B. So from the question itself, we already have this mixed surface contact angle, right? So for from the question we have theta is equal to around 75 degree. Theta A we have as 110 degree and theta B we have as 50 degree. And you have to actually determine the fraction of A. Isn't so? Yes, estimate the fraction of A in the mixed surface. So sorry, I lost my connection for a few seconds. So can you see? So cos theta is equal to Fa cos theta A plus Fb is Fb cos theta B. So in this mixed surface, let me represent 1 and 2 as A and B, right? So Fa cos theta A plus Fb cos theta B. So from the question itself, it's already given that the mixed surface is having the contact angle of 75 degrees. Whereas the contact angle for fraction A is 110 degrees and fraction B is 50 degrees. So you have to actually estimate the fraction of A in this mixed surface. Right. Till now it is clear. So is it clear or not? Then I'll move forward. Okay, let's see what. So you have to just put the values, and for that what we will do is, so cos theta, this is your main formula here, right? So cos theta would be cos 75 is equal to Fa cos theta A would be cos 110 plus Fb cos theta B would be 50, right? So what the thing is, so fraction A plus fraction B is actually 1. So you can write fraction B as 1 minus fraction A. Can we? So actually what happens is, in the mixed surface, the sum of both fraction is actually 1. Okay. So Fa plus Fb would be equal to 1. So we can write Fb as 1 minus Fa. Isn't it? Now just if we substitute the FB with 1 minus FA, what we will get is cos 75. We have to substitute this in this equation. Cos 75 is equal to FA cos 110 plus FB would be 1 minus FA cos 50. Is it clear? You can take it to next slide actually. So what did we get was, we got, let me write it once again. So cos 75 is equal to FA cos 110 plus 1 minus FA cos 50. So just you have to solve this. So how much is cos 75? It will be around 0.2588 FA, and how much will be cos 110? It would be minus 0.342 something plus 1 minus FA. How much is cos 50? 0.643. So can you understand it? Okay. So let's see. You have to just solve this. So it will become 2588 minus 0.342 FA. So if you open the brackets, what will we get? We will first multiply 1 with 0.643 and then FA with 643. Right. So 1 with 643 will be 0.643 again. And since there is a minus sign here, so minus 0.643 FA. Now just take these two on the left hand side and these two on the right hand side. So minus will here become plus. So 0.342 FA plus 0.643 FA will be equal to 0.643 minus 0.2588. Right. Any confusion or any doubt? So you have to just add these two on the left hand side and subtract on the right hand side. Then divide the ratio and you will get the answer of FA. Isn't so? Okay, let's see. So we have to add these two. So it will come around 985 FA and subtract these two. So this will come something 3842. FA is equal to 0.3842 divided by 0.985. How much did you get? Can you just verify? So we'll get FA as 0.39. So fraction of A is 0.39. Any doubts? So this was the answer. So you can verify it and ask me if you have any doubts yet regarding this question. So you all know, right? You can access all these files from the portal. I have already shown it. You can also access the YouTube link. So as the question stated, you have to estimate the fraction of A in the mixed surface. So the correct answer would be B, 0.39. Is it fine? Uh, so we first, through Cassie equation, we can determine the fraction of A, which came out to be 0.39. So that was all for today. So this was the last lecture. This was the last problem solving session. Again, if you still have any queries or doubts, you can go to the discussion forum and post your questions there. Right? So if there is no doubt, we can wrap up the session. Any doubts? Okay. Okay, you can leave now. Thank you for attending today's session. Good night for today.